Okay, so let's go over what I wanted to go over was this type of series, which is called a geometric series. So let's go, yeah. Next type is geometric series. And in general, this is the general format for a geometric series. So notice that and A and R are fixed, N is changing, right? So sometimes it's tricky because you're not sure what is changing, but the index is N, and that's indicated down here. Okay, so this is called a geometric series with a ratio R. Okay, now what we want to explore is we want to explore under what circumstances does a geometric series converge. Now, we have set up, and just looking at the series, the terms are a times r to the n. And the partial sums then, how do we get that? We're going to add the first n terms, right? So a1 plus a2 all the way up to an, right? And now just substituting, that means we'll have a plus a times r plus ar squared all the way up to a times r to the n. The next step, we can factor out an a. When we factor out a, we're left with 1 plus r squared plus r cubed all the way up to r to the n. Now, we actually have a formula to simplify this in yellow. So let's look over here. Do you remember how 1 plus r times 1 minus r is 1 minus r squared, right? Difference of sums. And then if we had 1 minus r, let's just show this. So if we had 1 minus r times 1 plus r squared, that's actually going to give us 1 minus r cubed. How do we get that? 1 times 1 is 1. 1 times r is r. 1 times r squared is r squared. Minus r times 1 minus r squared minus r cubed, right? So the inner terms will cancel out and we're just left with 1 minus r cubed. So this is the pattern. If we had 1 minus r times 1 plus r squared plus r cubed, we would get 1 minus r to the fourth power, right? So the formula is 1 minus r times 1 plus r squared plus r cubed all the way up to r to the n minus 1 is equal to 1 minus r to the n. Okay, so as we can in fact rewrite this formula a little neater, we can rewrite it by saying 1 minus r times the sum of r to the k. K starts at 0 and stops at n minus 1 is equal to 1 minus r to the n. Now, we're going to use this because this is our S sub n, is the sum of r to the k from 0 to n, right? And looking at this formula, we have two cases. If r is equal to 1, then this just ends up being a times n plus 1 because we've got 1 plus 1 plus 1 plus 1 plus da 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 all the way up to plus 1. And we have n plus 1 ones. If, on the other hand, r is not equal to 1, then we can go back to our formula over here and divide both sides by 1 minus r. That's what I did up here. Divide both sides by 1 minus r to get that 1 plus r all the way up to r to the n minus 1 is 1 minus r to the n over 1 minus r. The only difference for us is we'll have 1 minus r to the n plus 1 because our last exponent is n, right? So the formula that we have tells us that if n minus 1 is your highest exponent on the left, then on the right you should have n. So for us, we've got n on the left, so we'll have n plus 1 over here. Okay, so now why did we want to compute this? Because remember, our definition for the limit of this series, or the sum of this series, is based on looking at the limit of the sequence of partial sums, right? So we need to compute the limit as n goes to infinity of s sub n, and we've got our formula for s sub n here. It's either this or this. First, let's figure out what happens if r is equal to 1. If r equals 1, then we're looking at the limit as n goes to infinity of a times n plus 1. For the a times n plus 1, the n plus 1 is going to approach plus infinity as n goes to infinity, right? So, if r is equal to 1, then our series diverges. So you see that? What happens if r is not equal to 1? We need to compute this limit. So if r is not equal to 1, then the limit is n goes to infinity of s sub n is going to equal sorry, I'm trying to adjust this so you can see. Okay, if r is not equal to 1, then we're taking the limit of Sn. But remember, Sn is going to be a times, I don't know if you can see where I'm pointing. So this is our formula for Sn if r is not equal to 1. We are substituting that for Sn here. So we'll have, now I just pulled the a over 1 minus r. I pulled that out, and then I'm left with 1 minus r to the n plus 1. Okay? Now, a over 1 minus r, that's just a constant. It has nothing to do with n, so we can pull it out to the front. So that's how I have the a over 1 minus r out here to the front. And now I need to compute the limit as n goes to infinity of 1 minus r to the n plus 1. So I've got to figure out what is this limit. And in order to compute it, let's remember that r to the n plus 1 is going to go to 0 if r is in between negative 1 and 1. So the idea here is think about a fraction. It's like if you had 1/2 to the n.
It's 20 to 30.
That 1/2 is going to get smaller, 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 smaller. And you're going to go to 0. If r is bigger than 1, then r to the n plus 1 is going to go to plus infinity. And lastly, if r is less than or equal to negative 1, then r to the n plus 1 is going to diverge and it's going to oscillate, right? So it's going to oscillate in between plus and minus because r is a negative number, right? And it's getting bigger, but the sign of r to the n plus 1 is oscillating. So this is going to allow us to compute this limit based on this information down here. The only way this limit exists, so this exists only when r is in between 1 and negative 1. And so let me actually be a little clearer here. So altogether, this together exists, right? Only when r is in between negative 1 and 1. Because if r is equal to 1, then we will be dividing by 0 here. We'd be dividing by 0, and we can't do that, right? So let's write that over here. And in conclusion, so our geometric series converges only when r is in between negative 1 and 1. So we've got that here. And when r is in between negative 1 and 1, this is going to go to 0. So this limit as n goes to infinity is just going to be equal to a over 1 minus r. Okay? So the conclusion, and this is really called our geometric series test, is that the geometric series is equal to a over 1 minus r, but this is only valid when r is in between -1 and 1. And another way to say that is to say that the absolute value of r is less than 1. Okay? Otherwise, if the absolute value of r is bigger than or equal to 1, then our series diverges. So let's look at a couple of examples. The first example here is pretty straightforward because looking at it, we can tell right off the bat that a is equal to 1 and r is equal to 3/2. Geometric series test tells us if the absolute value of r is bigger than or equal to 1, the series diverges. So our conclusion is going to be that our series diverges. Let's look at this example here. Now, in order to do this example, I had to rewrite it. Turns out that a is equal to 3 and r is equal to 1/2. Now, how did I get that? I took this 3 over 2 to the n, and I wrote it as 3 times 1 over 2 to the n. And then I rewrote that as 3 times 1/2 to the n. So here it's clear to see that this is our r and this is our a. Okay? Now, if r is equal to 1/2, that means that the absolute value of r is less than 1. So our series converges, and we can compute the sum. The sum is going to be, remember our formula is a over 1 minus r. So for r equal to 1/2 and a equal to 3, we have 3 over 1/2, which will give us 6. Okay, so we said that we have typical problems involving geometric series. So the two that we did here are typical, right? And we have two more which are a little more complicated here. We'll look at, so this one and this one. And then lastly, there are word problems. So we'll look at a word problem. That'll be our final example. Okay, so let's look at this first example down here. And for this first example, the key is that we need to change the terms. So we're working on changing the terms. So we need to change the terms around a little bit so that we can actually end up with a geometric series. Because as it's written right now, we don't have a geometric series, right? Just looking at it, we need to rearrange the terms. How do we do that? For the denominator, that 3 to the n plus 1, rewrite it as 3 to the n, and then just times 3 over here. Now when we split this up, we've got 1/3 times pi to the n over 3 to the n. Okay? And we can take it a step further and write it as pi over 3 to the n. So from here, we can see that r is pi over 3 and a is 1/3. Okay? Now, once I know the r is pi over 3, I'm going to automatically say that my series diverges because the absolute value of pi over 3, which is the absolute value of r, is bigger than 1. And how do I know that? Because pi is bigger than 3. Let's look at the second example here. So this second example, let's pull this over here. Okay, so for the second example, the key is to change the index. Because look, we've got some funny business starting here. This is starting at 2. Oh, I deleted it. But do you see how this is starting at 2? And our formula starts at 0. Right? Our formula starts at 0. So we need to change the index. Let me write that in purple. So how do we change the index? Well, first thing we're going to do, actually we're going to change the index and we're going to change the terms. So the first thing I'm going to do is I'm going to write here, so I'm starting at 2. 2 to the 2n plus 1 over 5 to the n. I can rewrite this as, on top I can just have a 2, and then 2 to the 2n over 5 to the n. We can take it a step further. Now I have 2. Now 2 to the 2n, that's the same thing as 4 to the n. And in the denominator, I'll have 5 to the n. So now I've got 2 times 4/5 to the n. So basically what I want to do at this point is I want to change this 2 to a 0. So I'm essentially going to do a substitution. So if we let m equal n minus 2, then n equals 2 if and only if m equals 0, right? So it's just like when you're doing a u substitution. So we just have to switch everything over from m to n. So down here, I've got m starting at 0. And here I've got 2. This n, what is n going to be? Well, now look, if m is equal to n minus 2, that means that n is m plus 2. So I can write this as 4/5 to the m plus 2. Okay? And now, rewrite this as 2. I can pull off 4/5 squared and be left with 4/5 to the m. Okay? So, what is that? 2 times 16 over 25, which is 32 over 25. So I've got 32 over 25, and then I've got 4/5 to the m, starting at 0. So I can tell that my a is equal to 32 over 25, and my ratio is 4/5. So I use my formula to say that this is going to be equal to 32 over 25 divided by 1 minus 4/5, right? Since the absolute value of r is less than 1. And I can simplify this further if I wanted to. I can simplify this, right? So it's 32 over 25 over 1 over 5. So let's go on and simplify it. 32 over 25 divided by 1 over 5. Multiply the top and the bottom by 5. And I'll get 32 over 5, which is like 6.4. Okay? So this ended up being equal to 6.4. Okay, so what are the typical types of problems involving geometric series? This is plain old regular. You're starting at 0. You don't really have to do anything but identify a and r, right? Then it gets a little more complicated because you might need to change the terms. You might have n's and n plus 1s, right? So you might need to rearrange. And then it could get really challenging where you've got to do work with changing the index, right? So the index is what we call n. We did a substitution and we switched our index to m so that we are in a form where we're starting at 0 and we've got an r to our index times a constant, right? Because that's what we need in order to be able to apply our formula. So the last example I want to go over is the example here. It is a word problem. It is it's written very small. So I'm just going to try to zoom in here. So a ball is dropped from a height of 6 feet and begins bouncing. Okay. The height of each bounce is 3/4 the height of the previous bounce. What is the total vertical distance traveled by the ball? So let's try to draw a picture describing the situation. So we have a ball. Maybe it's a basketball. I don't know. I don't think it's a baseball because those don't really bounce. But okay, so say we have a ball. And the ball starts off. What do we say? We said the ball is going to be 6 feet. Yeah, so it has a height of 6 feet. So that means the ball starts off with this height here being 6 feet. Now the ball is going to, so first it goes 6 feet down to the floor. So this is the floor. Now it bounces back up, and it bounces at 3/4 the height of the previous bounce. So it's going to bounce back up. But now how far up is it going to bounce? It's just going to bounce 75% up. 75%. So I need 3/4 of 6. And that is going to be, say, 18/4, which is 9/2. So this is now 9/2 in this direction. So we're trying to compute the total vertical distance, right? That's traveled. So it's going to go up 9/2, but then the ball is going to come back down 9/2, right? And now it's going to bounce back up. And when it bounces back up, how high is it going to go? Well, we need 3/4 of 9/2. That's going to be 27/8. So it'll go up 27/8, come down 27/8. And the idea is that it keeps doing this, right? So it's going to bounce. And our goal is to figure out what is 6 plus 9/2 plus 9/2 plus 27/8 plus 27/8, right? So this is the ball coming down. This is the ball going up and coming down, and then going up, coming down, right? Going up. What's the next sum? The next sum will be 3/4 of the 27/8, right? And then going down, 3/4 of 27/8 plus dot dot dot. And all this is being repeated. This is being repeated forever, right? So that's our question, is we've got to figure out what is this equal to. Okay. Now, first thing we should do is we should separate it, because we've got 6 plus, that'll be 2 times, this was 3/4 of 6, plus 2 times, then we needed 3/4 of 3/4 of 6, plus dot dot dot. And each time we're taking 3/4 of the previous height, right? This 2, this factor of 2, comes from the fact that the ball has to go up and down, right? So we're getting twice the distance. And then the 3/4, each time we're multiplying by 3/4 because you're only traveling 75% of the distance of the previous bounce. Okay. So remember we said we'll have 6, and then plus, it looks like we need the sum of, so each term will have a 2 and a 6, right? A 2 and a 6. So it'll be 2 times 6. And what's changing is how many powers of 3/4 we have. So it'll be 3/4 to the n. N starts at 1, right? So we're starting here as n1. This is n is equal to 2. N is equal to 3, so forth and so on. This is what we need to compute. So we could rewrite this as 6 plus the sum, n equals 1 to infinity. And we'll have 12 times 3/4 to the n. Now I'm going to re-index, and remember how I re-index. A quick way to re-index is what you do on the outside, you do the opposite on the inside. So here, if I'm going to subtract, then I'm going to add 1. So if I subtracted 1 to my index on the outside, then I'm going to add to my index on the inside. So I have 12 times 3/4 to the n plus 1, right? I can peel off a 3/4 so that I now have 3/4 to the n, 0 to infinity, plus 6. So this is just going to be, what is that? So the 4, that'll be a 3. So that'll be 9 over 4. We have this, and then plus 6 times 3/4 to the n. So we've got 6 plus the sum, 9 over, what was it? 9 over 4 times 3/4 to the n. This is n equals 0 to infinity. And now my a is equal to 9/4. My r is equal to 3/4. So since the absolute value of r is less than 1, my series is equal to 9/4 over 1 minus 3/4. So this is going to be 9/4 over 1/4, which is 9. So my final answer which was copy, paste. So this was my final answer, was this. But now this part right here is equal to 9. So I get 6 plus 9, 15. So the ball total vertical distance is equal to 15 feet. Okay. So this gives us an idea of, this word problem gives us an idea or an intuition about why r is called the ratio. So in this case, ultimately our r was equal to 3/4, right? So our r was 3/4, right? Because that is the ratio of, that's the ratio of one term to the next, right? So a sub n plus 1 over a sub n is equal to r. So r is referring to the ratio of successive terms. Okay, that's it.